All right, this is going to be 3.2, and it's called Least Squares Regression. It says here that a regression line is a line that describes how a response variable y changes as an explanatory variable changes. A regression line is also called a line of best fit or a least squares regression line. Okay. We use a regression line to predict the value of y for a given value of x. A regression line is a model for the data. So going back to the last note card, all right, if you remember, we talked about that example with football teams, points per game, and wins. So this imaginary blue line that I put in here in the middle of all the data, that is the regression line. Okay? It's a model for what's happening. So what do I mean by model? Well, here's kind of what I mean. If this line is good, or let's say it is the best line that I could draw in between the points, well, one of the teams, Ole Miss, they averaged, I believe, 16.1 points per game, and they had 2 wins. But if I took this 16.1 points per game up until I got to the regression line would have predicted that they would have actually won somewhere between 3 and 4 games. So the regression line lets us make predictions. So none of the teams averaged, none of the teams averaged 22 points. How many wins would we predict for a team that averaged 22 points? Well, if we come up here to see where it would have hit on the regression line, and then if we take it over, we would have predicted they would have probably won somewhere close to 6 games. Maybe like 5.8. That's what we would have predicted. So the regression line gives us a way to predict. So, it says calculating y-intercept and slope. You will never be asked to calculate the equation of this line by hand on the AP test, but it is important that you understand the formulas that are given on your formula sheet. It is much more probable that you will be given a computer output. You'll see what that looks like here in a few minutes. Computer output, you need to interpret the given information. Your calculator will calculate the y-intercept and the slope of a least squares regression line. Okay, so here's the general form. If you remember back in algebra, we are so used to saying y equals mx plus b, or the y value equals the slope times x plus the y-intercept. In statistics, we like to put those terms backwards. Okay, so here, the b1 is next to the x, so the b1 is the slope. We like to list that second instead of first, like it's first over here. M is the slope here. Well, here we call b1 the slope. And we like to put the y-intercept first. Okay, and this y hat just stands for predicted y, because it's not the actual y. Going back to the graph example, the actual, like for Ole Miss, 16.1 was the x value. The actual y was 2, but the predicted y would have been slightly more than 3. That's why we call that y hat. This would be the y hat value, maybe about 3.1 or 3.2. So how do you calculate the slope of this imaginary blue line? Obviously there's some sort of slope. Okay, you could rise a certain amount and run a certain amount. You know, so if I put 2 points on here, I could rise a certain amount and run a certain amount. That would be the slope. Okay. Well, there's a formula to help us out. here's the nasty formula. Here's one version of the formula. And here's another formula. So if you have all the data, you can use this one. But if you know R, Sy, and Sx, you can use this one. Now, after you find B1, after you find the slope, you have to know that first. But as soon as you know that, now you can find out the Y-intercept by using this formula. What's most likely going to happen on the AP test, if you have questions about these, remember you'll have the formula sheet, so you'll have these formulas with you. They might give you a couple of the numbers, like they might ask you what B0 is, but they would give you Y bar, X bar, and B1. All right. So here's a very important distinction here. All right. The signs of slope and R will always match. So for instance, if R is positive, then the slope, which we call B1, that will also be positive. If R is negative, B1 will also be negative. So looking at this graph, if you remember back in the previous note card, the R value is about 0.936 for this data. Notice that's positive 0.936. What do you notice about this blue line? It's going up from left to right, so it would have a positive slope. B1 would be positive. Now, it's very likely on the AP test that you're going to have to interpret the meaning of the Y-intercept and slope. All right. So it says in algebra, what is a Y-intercept? It is the value of Y when X equals 0. In statistics, sometimes the Y-intercept has meaning and sometimes it does not, based on the calculated value. If you were asked to interpret the meaning of a Y-intercept, you would say, but before we do that, let me go back to this graph. What would the Y-intercept be? If I were to extend this line, down, let's see, that would be -1, -2, -3, that would be -4. So if we were to extend this regression line down until it hit the y-axis, the y-intercept here would be -4. What does that mean in this example? Well, if a team scores 0 points per game, think about this point right here. This has a coordinate value of 0, -4. If the x is 0, if the team scores 0 points per game, this line would predict that they would win -4 games. Now ask yourself, does that make sense? Can a team win -4 games? No, it doesn't. Okay. So this value would not have any real meaning. Sometimes it will, sometimes it will not. Okay, we know that if a team scores 0 points per game, they never score all season, they're going to win 0 games. Okay, so this does not have meaning. All right, so here's how we would explain it. When the points per game equals 0, we would predict that the number of wins equals -4. And then I would mention this does not have meaning because a team cannot have -4 wins. All right. So now what is slope? Just a reminder, it's a rate of change. We're used to writing slope as rise over run or delta y over delta x. So when we look at this blue line, okay, maybe we can estimate it from here. All right. If I go over, let's say I go over from, I don't know, this point looks like it crosses at a nice coordinate value. All right, if we go over 1 unit, how far do I have to go up? Okay, how far do I have to go up? Well, to me, it looks like if I go over 1, I'm going up 1. Or if I rose 1, I'd have to run 1. So to me, it looks like the slope is about 1. The value of it would be about 1, because 1 divided by 1 is 1. All right. So let's think about what that's saying. If the points per game, if a team was to get 1 more point per game, we would predict that they would get a half of a win. Because if we take this over, there's actually 2 lines between 4 and 5 wins. So for every 1 point per game, we expect the team to get a half more win. So if you went over 2, you would go up a whole number of wins. Okay, so I really should have written this as, this wasn't 1, it was actually 0.5. Okay, so you're rising 0.5, running 1. So the value of the slope would be 0.5. For every 1 more point per game, we predict the team would win 1 more game, roughly. Whenever we have a regression line, this slope always has a meaning. All right. We already said that if the slope's positive, R is positive, and vice versa. All right. All right. So how do you explain the slope? As the points per game increases by 1 unit, the response or you could say by 1 point, the number of wins is predicted to increase because it went up, expected to increase by 0.5 wins. 0.5 wins. All right. So here is the prediction equation. This is the prediction equation for our last example. All right, so this value right here is the Y-intercept. This is the slope, the 0.44. We predicted it to be 5. And we predicted that just looking at the line to be -4. So we were pretty close. Okay. So let's answer the questions. What is the value of the Y-intercept? The value of it is -3.75. Interpret that in context. If a team were to score 0 points per game, we would predict that team would win -3.75 games, which doesn't make sense because a team cannot win negative games. So I'm going to say that it doesn't have meaning. So what's the value of the slope? Well, the value of the slope is 0.44. It's positive because there's a plus there over an understood 1. Well, what's the 0.44? That's the delta y. What's the 1? That's a delta x. So it's like a plus and a plus. All right. So what does delta x mean? Okay, this is the points per game, and on the y-axis we put wins. So here's how we're going to interpret that. For every +1 points per game, so for every 1 unit increase in points per game, we would predict, you got to say predict because the line's a prediction line, that the x, or the number of wins, that the number of wins would, what's the value? Plus 0.44. So since it's plus, the number of wins would increase by 0.44 wins. Okay. So that's almost 0.5. So basically, like if this went up by 2, this would almost go up by a whole win. Okay. And let's do number 3. It says that suppose that in 2011, the SEC was contemplating adding a 13th team to their conference that averaged 21.2 points per game. Okay. So I didn't get rid of my data. My data is still in my lists. So right now I have 12 data points. And then if we looked at the scatter plot, there it is. Okay. Let's add let's add a 13th data point. So a team comes in, a new team to the SEC, and they score 21.2 points per game. So 21.2. Okay. Okay. It says predict the number of wins that this team would have based on the previous equation. So they didn't actually tell me how many wins this team had. So I'm going to get rid of that data real quick. Sorry about that. I just didn't look ahead. Okay. Sorry about that. So let's actually go back to our regression equation. Here was our regression equation. Regression equation. Wins equals negative 3.75 plus 0.44 times the points per game. All right, so what we're actually going to do here is this is a number of points per game. We could stick it in where that points per game is. So to predict the number of wins, we would do negative 3.75 plus 0.44 times 21.2. Okay, so I'm just going to put that into the calculator. Negative 3.75 plus 0.44 times 21.2. That's about 5.58. So if this team came in, we would predict that they would have 5.58 wins. And what does that mean on the graph? Let's look back on the graph at our prediction line. If another team came in with 21.2, here's 21. 21.2 is slightly more than that, maybe about right there. If you take that up and look at where it hits that blue line, okay, it's about right here-ish. Okay, which is a little bit less than 5.5. Okay, it's a little bit less than 5.5. About right there. All right. So that's what we're doing. But we can do it with arithmetic. We don't always have to make a drawing. Okay, we don't always have to make a drawing. Now, going back to the calculator. Okay, our data was in list 1, list 2, and we plotted our scatter plot. There it is. Okay. Now, let me change the window to match what we did on paper. 0 to 40, and we'll do 0 to 14. So that's what our scatter plot looks like. Actually, I'm going to change this a little bit. I'm going to make this go from negative 5 to 14. Our scatter plot's still there. Now, we talked about how we use the calculator to find the R value, the correlation coefficient. But we can actually find, how did I know that this was the right answer? How did I know that this was the equation of the regression line? Well, our calculator can do that too. All right, we go stat, remember what we did before. We went stat, calc, number 8, linear regression. My X list is in L1, my Y list is in Y2. Now I'm going to have you do one more thing. When it says store the regression equation, let's store the equation into Y1. So hit alpha, then use the shortcut, hit trace, and choose option 1, Y1. And now let's calculate. Okay, so what it does here, this wizard tells you A, they call it A here. They call it A the y-intercept instead of B0. But they tell you the value of that is negative 3.75. What do you notice right here? Negative 3.75 plus 0.44. The B here, it would be the slope. So you look at the B, 0.44. Okay, so that's how I get the y-intercept, which the calculator's calling A, and the slope, which the calculator's calling B. And if you store it into y1, if you hit y equals now that equation with all the decimals are stored in y1. So that negative 3.75 is the y-intercept, plus the 0.44 approximately. And if you hit graph again, not only are you going to get the scatter plot, you're also going to get the regression line drawn in there for you. And here's what's really cool about that. Okay, if you hit trace now it tells me that I'm on the scatter plot, but if you toggle down, you'll be on the line. And you can move up and down this regression line. If I type in that a team scored 21.2 points per game, like it told me, I can hit enter, and I can get the predicted value right away. This tells me that the predicted value is 5.518. This is the perfect answer because I stored all the decimals. This 5.58 is an estimate, but remember we're rounding off these two numbers. A better prediction would be 5.52 rather than 5.58. Now let's do another example of linear regression, but this time we're going to use a computer output. So let's read it. It says, for their second semester project, 2 AP Stats students decided to investigate the effect of sugar on the life of cut flowers. Okay. Sugar on the life of cut flowers. They went to the local grocery store and randomly selected 12 carnations. All the carnations seemed equally healthy when they were selected. When they got home, the students prepared 12 identical vases with exactly the same amount of water. They put 1 tablespoon of sugar in 3 vases, 2 tablespoons of sugar in 3, and 3 tablespoons of sugar in 3. In the remaining 3, they put no sugar. After the vases were prepared and placed in the same location, the students randomly assigned 1 flower to each vase and observed how many hours each flower continued to look fresh. A computer output from the regression is shown. So we basically have 2 variables. We have sugar. Okay, we have sugar, and we have, let's see, we have the amount of sugar, and that can either be 0, 1, 2, or 3 tablespoons. All right, and we have length of freshness, okay, the length of time, length of freshness in hours, that the flowers looked fresh. Okay. So let's figure out which one of these would go on the x-axis and which one would go on the y-axis. Which one predicts the other? I think that the amount of sugar that we put in the vase explains how long the flowers are going to look fresh. So I think this is going to be the explanatory variable, and this is going to be the response variable. So we would put that on the x-axis, we would put this on the y-axis. Instead of giving you the actual data, they can give you a computer output. Okay. So how do we read this computer output? What are the important things to pull out of there? Well, there's a few things. Okay. So right here, they're going to give you some variable name. Whatever name they give you right there, that's going to be the x variable. So the x variable is sugar here. What would that make the y variable? Well, the other variable, okay, this is the length of flower freshness. Okay, in hours. So as I start to write my prediction equation, remember it's y hat equals b naught plus b1x. Well, what is y? Y is the length of flower freshness. So instead of writing y hat, I'm going to say length of flower freshness. Predicted. The predicted length of flower freshness equals. Now, where do I locate the y-intercept? Remember, b naught or b0 is the y-intercept. Okay. Well, this is just a number by itself, which we usually call a constant. So to find this thing, to find b naught, next it's going to be the number next to constant. Okay, it's going to be the 181.20. Plus, okay, the b1 is the slope. Okay, the slope will always be next. Okay, just like b1 is next to x here, b1 is next to x here. So we have plus 15.200, but instead of saying x, let's write what x represents. X represents the amount of sugar. So let's see what we've done. We gave the equation of the least squares regression line, that's this thing, in context. What does it mean in context? I put actual words in here instead of y and x. I need to do one more thing. It asked me to interpret the slope and the y-intercept. So which one of these numbers is the y-intercept? This is the y-intercept. All right. So if you think about this graph, it hits at 181.2. Okay, that's where it hits the y-axis. And it has a positive slope, so it's going to go up from there. So what does that mean? What is the x? On the x-axis we put sugar. So what is the meaning of that? When we add no sugar or zero sugar, when we add no sugar, we predict the flowers would appear fresh for 181.20 hours. That is the meaning of the y-intercept. Now, does that make sense here? Yes, it does, because on several of our vases, we didn't put any sugar. So it does make sense. Okay. Now, what is the meaning of so this is the interpretation of the y-intercept here. That's how we interpret it. When we add no sugar, we predict the flowers would appear fresh for 181.20 hours. Now, what is about this slope, this 15.2? That really means, I'm going to do it up here, that really means 15.2 over 1, which is change in y over change in x. All right, and both of those numbers are positive. Okay, so how would we interpret this? For every time x changes by 1, so for each 1 additional tablespoon of sugar, so that's what this thing represents. For each 1 additional tablespoon of sugar, we predict that the flowers would appear fresh for what? And for a positive 15.2 hours. Would appear fresh for an additional 15.2 hours. And that is the interpretation of the slope. For each 1 additional tablespoon of sugar, we predict the flowers would appear fresh for an additional 15.2 hours. Okay. That's the meaning of the slope in this problem. So when we need to find the regression equation, it's just these first 2 numbers. In red, there's the y-intercept. In blue, there's the slope. That's all it is. More about prediction. It says extrapolation is the use of a regression line for prediction far outside the interval of values of the explanatory variable. Such predictions are often not accurate. So going back to our football example, here's our football example. The team that scored the least amount of points per game they only had, about 15.8. Okay, Kentucky. That was Kentucky. They had 15.8. And the team that had the most points per game, all right, had this 36 point something. That was Arkansas. 36.8 was Arkansas. So it makes sense if I were to take this down, take this one down, all right, that had a value of 15.8. That was Kentucky. And the one that had the most points per game were Arkansas. If I were to take that down to where it hits the x-axis, then that was 36. Let's see, Arkansas 36.8. 36.8. All right, so it's fair for me to make predictions as long as I'm plugging in team values, as long as I'm plugging in points per game between these numbers. Okay, it makes sense to make predictions for SEC teams if they're between that many points per game. Okay, what that's called is interpolation because it's inside the domain of X. Now, if we had a really weak, another really weak SEC team, let's say we had an SEC team that only scored, 10 points per game. 10 is pretty far away from 15.8, somewhat. Okay, it wouldn't be fair for me to make a prediction for the team that scored 10 points per game. Okay, because what I'm doing is I'm outside of my values that I was given. So if I make a prediction here, then that's what's known as extrapolation. Okay, because I'm extrapolating the line beyond the data that I was given. All right, it can be dangerous to do this, especially if you're really far away. The farther away I get from 15.8, my prediction might not be as accurate. If I had another team here, like a superior football team like Ohio State, all right, it might not be fair to remember, like if this line kept going up, and if you have a team that scores like 60 points per game, even if a team scores 60 points per game, they're not going to win 18 games or whatever it would come out to, because there's not that many games in the season. So it wouldn't be fair to me for me to make a prediction way out here either. So I don't want to really make predictions that much higher than 36.8, and I don't want to make predictions much lower than 15.8. It's not fair to do that. And that's what extrapolation is. All right. So a residual is the difference between an observed value of the responsive variable and the predicted, and the value predicted by the regression line. So the residual is the observed y from the data minus the predicted y from the regression line. So let's go back to our example so you can understand this. Okay. So most of you are probably Alabama fans. That's okay, nobody's perfect. So here for Alabama, this was Alabama. Okay. That point represented Alabama. All right. So Alabama averaged 34.8 points per game, and they won 12 games in 2011. But what about the value? What would the value be if I plugged 34.8 into the prediction line? Well, let's go back to our graph here. Okay, so here was our line. Let me zoom in a little bit. So I'm on my line now. If I type in 34.8, the prediction line says 11.46. Okay, so this right here, the prediction line predicts that Alabama should win 11.46. Predicts that Alabama should win 11.46 games. All right. Clearly, there's a difference here. Alabama actually won 12 games, but our prediction line says that Alabama should have won 11.46 games. Okay, so there's a little bit of a difference here. Okay, the length of this right here is a difference. It's a difference between prediction, there's the prediction, and the observed. Okay, so all of these points that fall above the line, they did better than expected. Okay, if you take their distances, their vertical distance between the point and the line, they did better. The teams that are underneath the prediction line, they did not do as well as expected. And you have some teams that are really close to the line, and some teams that are a little bit further away. Like this one right here is pretty much right on top of the line, that one right there. Okay, and then this one is kind of farther away, this one not too far away. So this distance has a name, the distance between the observed and what would be predicted. That's called a residual. So every point has its own residual. The way we calculate it is we take what was observed, like Alabama's actual. Okay, so in this case, the residual for Alabama, they actually won 12 games. But the line predicted that they would have only won 11.46 games. So if I subtract those, I would get 0.54. So on the graph, this distance is 0.54 units, okay, or 0.54 wins. Alabama did 0.54 wins better than we expected them to do, based on the other team's data. So it says each data point has a residual. And just like we talked about, that's the vertical distance. Now, something special happens about the residuals. If we were to add up all the residuals for all the points, it's always 0. It has to be 0. Otherwise, it's not a good line. All right. And we'll talk more about this in class, but the best line, the reason why it's called a best fit line, is because it's the line that if I took all the residuals and I squared them, it would be as small as possible. Okay. And you can read this more on your own. But let's actually get into calculate. How do I calculate the residual for each team? And we're going to use our calculator on this. Okay, we're going to use our calculator. So we just did Alabama, right? The predicted wins for them were 11.464. All right. What's the predicted wins for Arkansas? How do I find that? Well, on my graph, okay, if I type in 36.8, Arkansas was predicted to win 12.339. Hopefully you guys saw that right here, 12.339. All right. What about Auburn? If I type in 25.7, the prediction line says they should win 7.486. Okay. When I type in 25.5 onto my line, Florida should win 7.398. Georgia, when I type in 32.0, the value on the line is 10.240. When I type in Kentucky, 15.8, The prediction line says that they should win 3.157 games. So let's calculate the residuals for these first 6 teams. You take the actual, which is also the observed, okay, minus the predicted. So what's 12 minus 11.464? Well, that's 0.536. Okay, to 3 decimal places this time. What's 11 minus 12.339? Well, that's negative 1.339. Okay, 8 minus this would be 0.514. 7 minus this would be negative 0.398. 10 minus that would be negative 0.240. Really, I should put a 0 in front of that, sorry. Okay, 5 minus that would be 1.843. Let's keep going. On the next page, there's the other 6 teams on here. All right. So for, this was LSU, sorry, kind of got cut off there. That's LSU, that's Ole Miss, that's Mississippi State, that's South Carolina, that's Tennessee, and this is Vanderbilt. Okay. So LSU 35.7, so if I type in 35.7, they were predicted to win 11.858. When I type in 16.1, comes out that Ole Miss was predicted to win 3.289. When I type in 25.3, predicted wins are 7.311. When I type in 30.1, the predicted wins are 9.410. When I type in 20.3, it's 5.125. When I type in 26.7, 7.923. If I do my subtraction, actual minus predicted, LSU overperformed. They won 1.142 more games than we expected. 2 minus this is negative 1.289. Ole Miss won, or they won 1.289 less games than we expected. 7 minus that would be negative 0.311. 11 minus that is 1.590. 5 minus that is negative 0.125. 6 minus that is negative 1.923. Okay. So again, these red numbers, I'm going to kind of show them to you side by side. All right. These numbers in red, that's the residual for each data point. On the graph, it's the vertical distance. Okay, it's the vertical distance between the point and where the prediction line is. Okay. So of these, let's look at it. Which one is the biggest positive? Okay. Here, South Carolina, they have a residual of 1.59. 1.59. Oh, sorry. Kentucky has 1.843. So looking back at this graph, here was the point for Kentucky right there. Okay. Do you see how big that line segment is? that distance is 1.843. All right, South Carolina had about 1.5. Those were the biggest residuals. Okay, looks like these two are the most negative residuals. Okay, these two. All right. So here, which ones are the biggest negative residuals? Well, it looks like Ole Miss underperformed, all right, and Arkansas underperformed based on their points per game. All right. Now, like I said, the residuals should add up to 0. So if I add these red numbers together, they should come out to equal 0. So let's try it. So I'm just going to do it in the calculator. So you can do that too. Do 0.536 minus 1.339 plus 0.514 minus 0.398. Now before I get my answer, I might be slightly different than 0 because of rounding. Okay, minus 0.240 plus 1.843 plus 1.142 minus 1.289 minus 0.311 plus 1.590 minus 0.125 minus 1.923. And what do you know? When I put all those in, when I add up all those red numbers, all 12 of those red numbers, it gives me 0. It gives me 0. Now, we could have actually done, there's an easier way to do this. There's an easier way to figure out what the residuals are. Now remember our graph. We made our scatter plot after we put in our data to list 1 and list 2. We did our linear regression and got our regression line. So we've already done linear regression. After you do linear regression, the calculator will actually store the residuals for you. The calculator knows what these vertical distances are. So here's how you can display them. Go back to your list, so go Stat Edit, and up in the title for L3, I want you to display your residuals. Here's how you do it. Go second, and then in blue above the Stat button says List. Okay, if you scroll down, you should see a list that says L Resid, or just Resid. There it is. Okay, choose that one, so hit enter. So when you do that, I'm telling, okay, calculator, in list 3, I want you to display the residuals for me. So what do you notice? This first number, 0.5355, guess what? That was Alabama. That was 0.536. That was its residual. What about Arkansas? Negative 1.339. There's the residual for Arkansas. So it gives me all of these residuals for every data point. Okay. This list shows me the residuals. Okay. It shows me the residuals. So now we're going to talk about a residual plot. Okay? And a residual plot is the best way to determine if data is really linear. Okay. So here's how you make a residual plot. So in our points per game, okay, our points per game, it pretty much started at 15. Okay, the team that scored the least amount of points had 15 points something. So 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Okay. So on this axis is still the x value. So this is still points per game. But since this is called a residual plot, instead of putting wins up and down the y-axis, we're actually going to put the residual values. Okay. So looking at some of the residual values, some of them go up to about 2. Okay. Some of them go up to about 2. Some of them go down to about -2. All right. So I can put maybe like +1 there, +2 there, and I can, I can subdivide it a little bit more. So I can subdivide it by 2/10. Each tick mark is 2/10. I can do the same thing here. 2, 3, 4. That's -1. One, 2, 3, 4, 5. That's -2. So I'm actually going to plot the points per game versus the residuals. So basically what I'm doing is I want to make a plot of my data from list 1 and from list 3. Okay. So just looking at the data again. Okay, we'll start on the first page of that, on page 7. All right, so Alabama. Alabama scored 34.8 and it had a residual of 0.536. Okay, so 34.8, that's about right there, and its residual was 0.536, so 2, maybe about right there, if I'm plotting it. All right, and then Arkansas had 36.8, there's 36.8, had a residual of -1, okay, about -1.3. So there's -1, 2, 3. All right. So you could keep going. All right. So Auburn 25.7, residual of 0.514. So that's about right there. Florida 25.5, residual of about -0.4. So that might be about right there. Okay, Georgia 32 points per game, residual of -0.2. So 32, -0.2. Kentucky about 16 points per game and about 1.8. So about 16 and about 1.8. So we plotted 6 of the residuals. LSU 35.7, 1.14. Be about right there, give or take. 16.1 for Ole Miss, 16.1, negative about 1.23, or 1.3, -1.3. The idea is just to get close when you're doing it by hand. All right, Mississippi State 25.3. -0.3. So that's about right there. South Carolina, 30.1, which is about 30, and about 1.6. Right there. Tennessee, 20.3, -0.125. 20.3, -0.125, which is very, very close to 0. And not even a tick mark down. Bandy 26.7, 26.7, negative 1.923, which is almost negative 2. So maybe about right there. So let's make sure we got all 12 teams. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just again, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what do you notice about this residual plot? There's no pattern. That's a good thing. If there's no pattern, I'm convinced that the original data, original points per game versus wins data, is linear. Right. So how do you do a residual plot on your calculator? Well, after you run the regression, which we've run the regression, what we can do is go under our, before we do this, let's go ahead and turn the equation of the regression line off. Now let's go under our stat plots. Now here's what we want to do. We want to make another scatter plot, but it's actually going to be a residual plot. So our X list, we put our L1 data just like before, but the Y values here need to be the residual values. Well, where are the residual values? The residual values are stored in the residual list. Do this one in green. So if I do that and then hit zoom 9, here's what my residual plot looks like. Okay, 1, 2, 3. Those are these 3 points. Okay, then the next few are 4, 5, 6, 7. 4, 5, 6, 7. Those are those 4 points. All right, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11, 12. So there's the last set of 5 over here. And it looks just like it does on the calculator. Again, what we're looking for in a residual plot is we're looking for no pattern. Okay, we want some above, we want some below. Okay, and we want to see random scatter. That's what we're looking for. We're looking for no pattern and we're looking for random scatter. If we had a graph, if we had a residual plot that looked like this, that would be bad because it doesn't appear like it's random scatter, it appears like it's a parabola. We don't want to see a scatter, or we don't want to see a residual plot look like a line because that's a pattern. So when we're looking at residual plots, we're looking for no pattern. Okay. So here's how we're going to say it. We're going to say the residual plot shows no pattern and random scatter. Therefore, we have confirmed that there is a linear relationship between points per game and number of wins. Because when we first just looked at the data, if you go back to the data before we drew in that line, if you remember way back when, okay, it looked like it was approaching linear, but we weren't sure. It doesn't follow directly in a straight line. It looks close to appearing, looks like these points are close to this line, but we don't really know. Okay, so that's what a residual plot does for us. Okay, we want to see no pattern and we want to see random scatter. Those are good things for a residual plot. All right, so when we ran our regression, before we drew the line in there, you probably saw this R squared thing that was right above the R in our calculator. Well, this R squared thing is called the coefficient of determination. Okay, it says the coefficient of determination is the fraction or the decimal of the variation in the values of y that is accounted for or attributable from the least squares regression line of y on x. To attain an R squared value, just take the value for R and square it. Here's the interpretation and saying that you need to know. So when we ran our linear regression, let's go back to that. So when I did stat calculate linear regression, that 8th choice, and my data is in list 1 and list 2, and I calculate, it gives me the r squared value. Okay. It also gave me r. So there's 2 ways to find it. You can take this r value, 0.9358694593, and that's what r is. So to find r squared, you could just have squared that. Okay. But I'm just saying, like, if they gave you r in a multiple choice problem, they asked you for r squared, you would just square it. But with a calculator, it gives me r squared already. Okay, that would be 0.8759 if I round. Okay, so 0.8759. Here's the meaning of that. Treat this like it's a percent. So here's our saying. We say 87.59% of the variation in what is the response variable, what's on the y-axis, in the number of wins. Okay. So 87.59% of the, what's another word for variation, spread, of the spread and the number of wins is accounted for by the linear relationship, okay, by the linear relationship with what is the explanatory variable, points per game. So that's the saying that we try to remember. The r squared value expressed as a percent of the variation in, so basically, here's the things that you're plugging into. It's like a formula for you to remember. 87.59% of the variation, the number of wins is accounted for by the linear relationship with the x variable, or the explanatory variable. So you just put those things in there. Okay. Now instead of saying the linear relationship, you could have said the least squares regression line, by the least squares regression line with points per game. That would have been fine too. So that is the meaning of r squared. So what does that really mean though? All right. So the natural spread that we get, okay, when we do this regression line, these points are not directly on the line, okay? If it was a perfect relationship, all of these 12 red dots would be on the line. If all 12 of the dots, or the blue line, excuse me, if all 12 of the red dots fell on the blue line, then r would equal 1 and r squared would also equal 1, okay? So there's 100%, in that case, there would be 100% of the variation in the number of wins can be explained by the points per game. Okay, so the spread is completely fixed. All right. This is still a big number. This is a very big r squared number. All right. So the higher this is, the more the data impacts each other. We don't want to use the word cause. They don't cause each other. But the higher this number is, the more they impact each other. The more the variables impact each other. That's the best way to say it. The higher that is, it counts for a big portion of it. 87.59% of a team's number of wins, okay, can be explained by their points per game. Okay. So 87.59% of a team's number of wins can be explained by how many points per game they score. That's pretty powerful. So if you're a football coach, you scored a lot of points. All right. So on to the last page of this section. It says an outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the y direction but not the x direction have large residuals. Other outliers may not have large residuals. Okay. So let's think about what that's saying. Outlier is an observation that lies outside the general pattern. So if here's my scatter plot, okay, if there's my scatter plot, a number is an outlier. This is the general trend. What about if we have another one that's right here? Another point that's right here. So generally, here's our least squares regression line. It's got a bigger residual than all these other points. Okay, it's got a non-typical residual. It's got a non-typical residual. All right. That's what this is saying. In the y direction, have large residuals. Other outliers may not have large residuals. Just depends. All right. So an observation is influential, sometimes referred to as an influential point for a statistical calculation, if removing it would markedly change the results of the calculation, most notably the equation of the regression line. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. So if we have some data like this, like kind of before, this would be considered an outlier. Okay, it would be considered an outlier. But if you have a point, okay, let's say you have a point way over here, okay, like a genius, you're measuring intelligence or something, all right, and you draw your, all right, if you didn't consider this point, imagine that without it, we could draw the regression line kind of in the middle of those points. But when we take this point into account, it changes the regression line so the slope isn't quite as steep anymore. And it might even move the y-intercept a little bit, but most notably the slope. Okay. What's happening here because of this, imagine this line went up higher, it would have a residual, but it would have a negative residual, so a lot of these smaller positive residuals have to make up for that negative residual. So that's what caused the regression line to move down. It can't be as steep anymore. So if the regression line changes big time, if the regression line changes big time, I know that's not very technical, then a point is influential. So referring back to our example, the SEC football example, suppose another data point was added for a 13th team. This team averaged only 45 points per game, or this team averaged 45 points per game, but only had 4 wins. So let me kind of go into here, let me delete everything. Let me go under my list here. Let me get rid of list 3. Let me get rid of my regression and my residuals. So I'm going to add a 13th team. That 13th team averaged 45 points, but only had 4 wins. Probably a team from the Big 12, because they don't play defense in the Big 12. All right. Now let's look at a regular scatter plot. Turn that on, make a scatter plot. Just a regular scatter plot, so L1 versus L2. All right, and zoom 9 in. Ooh, so we added this 13th data point. Look at that. Okay, it's way below what we expect, and it goes over X. So this might be an influential point and an outlier. Okay, now let's run regression on it. Okay, let's run regression. So before I do that, let's go back to the old data. Let's remind ourselves what it was when there were 12 teams. So when there were 12 teams, I'm going to have to find it. what did we have? We had the correlation coefficient, R was 0.936, R squared was 0.876, and sorry, I'm trying to find it. And the equation of the regression line was wins equal negative 3.75 plus 0.44 points per game. That was the old data. New data with 13 teams. I'm going to run the regression here. So quit out of there. I'm going to go stat, calculate number 8, list 1, list 2, store the regression equation, and calculate. All right, so let's write this information down. I'm going to take that information from the calculator and write it down. Well, the R now is 0.518. Look how much that changed. Look how much it dropped the correlation. It used to be very strong. Now it's barely moderate. What about R squared? R squared went from 87.6% down to 26.8%. Just by adding one more team. And what about the regression line? Predicted wins would equal, instead of being negative 3.75, now it's 1.86 plus 0.21 points per game. I'm not too worried about the Y-intercept, but look how much that changed the slope. It used to be for every one more point per game, we would expect a team to gain 0.44 wins. Now, for every point per game, we only expect a team to go up by 0.2 wins. So here it would take about 5 more points per game to get a win. Here, if you had 5 more points per game that you averaged, you would get 2 more wins. So this is almost double. All right, so by adding this team, I've actually cut the slope in half. So look at the line now. Okay, look at the line now. Okay. It used to be the line was a lot closer to these 12 points. Now, if you think about the residuals, each of the residuals seems bigger, and this one would have a big residual as well. Okay, so that one changed it dramatically. Adding that one extra team's data changed our regression line and our correlation coefficient and our coefficient of determination big time. Okay, so I would consider this an influential observation. I could say things like the slope got cut in half. Okay, slope got cut in half. The data is now only moderately okay. The data or the relationship now only has a barely moderate strength. Which changed from very strong. Okay, so that there's a big impact. Adding that one extra team changed it dramatically. So I would consider that an influential observation. Now, what about if it didn't go down by that? What about if it went from like 0.44 down to like 0.38? And maybe this went from 0.936 to 0.82. That's not as dramatic. So in that case, it's all a judgment call on your behalf, but outliers will change the values, but not this extreme. Okay, outliers will change them a little bit, but not that extreme. That's how you decide. So I'm not going to read the bottom part of this to you. It's just general and complete steps about bivariate data, how you do it in the calculator, and what you need to think about. So just read that on your own. Guys, I'm sorry this video took so long. It is important. Linear regression is a major topic on the AP test. So you need to feel really, really comfortable on writing the equations but more importantly, understanding the concepts associated with it. So video's long, but when you need help, go back and watch the parts that you struggle with, make a list of questions, and bring those into class with you. I appreciate you watching.